We are happy to present our effective and efficient solution to a control for friction stir welding. And as you know, friction stir welding is an important process where they heat a rod up and it plasticizes the two metals and creates a nice weld. So it's important for uniform welds to control the temperature of the tip of the rod. And so what we first did was section up the rod into 10 different pieces. And to perform a first principles model on the whole rod, we did energy balances for each of the sections. And this is the energy balance for the top of the rod where you input the energy. And the other ones are similar with a few minor differences. As you can see, the second one is for all the middle sections, and this third one is for the last section. And what we realized from this first principles model is that it was a complicated system, and it would be a complicated system after putting it into linear form into the Laplace form. And so we made some simplifications and throughout the radiation terms and made a model of the system and put it into MATLAB to generate, with its step tests, some data to fit it with a first order plus dead time model. And this, as you can see, the data from that step test to this model that we had. And we fit it, and you can see our values of 0.863 for our gain and our time constant of 463. And the most important and interesting thing is our dead time, which is 127 seconds. And that's more than what you wanted us to be able to heat it up to 400. That's over 2 minutes, and so that means for our process, in order to get it to 400 degrees Celsius, we can't do it that fast. So from there, we went on to start to implement a controller to see how fast we could actually get it up to.
And John brings up an important point, that the original hope was that we could do this within a 2-minute time limit, and that's obviously not going to be possible with the dead time that you see there. But we, having been trained on process controllers and methods, we feel we found a good solution to this, a better solution, not the best, since we can't meet that 2-minute time limit. So now we're going to take you through the process that we went through to find that best controller. So we originally started with a PID only controller, so we're going to pause before we get into the Smith predictor. And we noticed that the PID only controller is extremely slow. It took about 30 minutes using the controller values we got from IMC method. And this was kind of puzzling. How are we even supposed to get close to the 2-minute time limit? And so we decided, well, let's just up the gain. And in order to find out how high we could go, we did a root locus plot to see, okay, what is the range of Kc values that we can have. And we found it was from 0.8 to 8.5. Now, this brought up another struggle. When you go above 2.9, you're above the melting point at the top of the rod. This is a predicament because how do we control the end tip temperature if we're melting the top of the rod? And so after we looked around a little bit, we realized, it's common practice in industry to be able to put an upper limit on the output of a controller. And so we did that. Still, it only cut the time down to 2.7 minutes. And we realized that the physical limitations of our control process would not allow us to get any faster than that. What we needed was a model predictive controller. Because of the dead time, the controller can implement or output a change, but it will take so long for the actual sensors to detect the change that the controller applied. And so what we can do in a model predictive controller is we can have an ideal model giving feedback to the controller minus the dead time. And in this way, it gives the controller the power and the ability to sense or foretell, in a way, what will happen real time. This method is extremely effective for such cases where the conductivity, no matter how conductive your material is, it limits the amount of time, or it limits the time that the temperature gradient will change. And so this is extremely effective for our specific situation, and we'd like to show you the results. You'll notice in this blue line we have the PI only controller. Very slow. It looks good in terms of what a PI can do, but it's very slow. You see we reach steady state way out here. This red line represents the Smith predictor, and you notice it's a sharp 5 minutes. It's beautiful, really. I mean, it's pretty quick, right? And with the Smith predictor, we found that we could increase the gain to almost insane numbers, up to 300 sometimes, which is 2 orders of magnitude larger than the initial IMC controls. But this comes at a cost, and we'll talk about that in terms of how that affects the actual heater or the heat source you're using. But you'll also notice 2 other curves here. What are those for? Why would we put those in there? It is unreasonable to assume that every rod will have the exact same characteristics and material specifications as the one that we originally tested. And so it's important for this to be applicable in industry to have a range of values that this predictor will work over. And the purple line represents the plus 5% deviation, and the green line represents the minus 5% deviation. And you'll notice that we still had very responsive and good controls over this large window, and we feel that a 5% deviation is actually pretty large, especially given the high tolerances that these stir rods have in manufacturing. Now, this is not all that we need to consider. We need to consider the top temperature to make sure that A, it's not melting, and B, what is that heater having to do in order to get this tip temperature. And you'll notice that with the blue line you get a nice smooth curve, and we do max out at 400, and so that's important that we stay below that melting point. This is in deviation, since the melting temperature is about 1425. But you'll also notice that orange line drops down and just stays really constant. We found that the only way to reach that constant, nice level temperature, so meaning the heater's just putting out a nice, constant, consistent 400 degrees Celsius, just above it, I believe. The way we did that is to decrease the tau. The tau was originally 463. And if you don't decrease the tau, what you get is oscillations. Now I'm thinking in my mind that heater's got to go hot, cold, and it's just fluctuating. That's not going to be good for the element of the heater or whatever process that you're using. And so we tried to really iron out those oscillations. Now you notice in the purple and green line that wasn't completely possible with the deviations. But these do represent the best fits from our experience. The deviations were smaller, and they dampened out rather quickly relative to the other control parameters we found.
So in conclusion, we first developed a first principles model of our system and looked at linearizing it through a Laplace transform of those equations, and saw that might be too difficult, involving lots of differentials. And so we went to fit a first order plus dead time model to a step test, and we got that model and implemented a PI controller and realized that it doesn't really control the process and takes a long time to get there, and saw that, as Devin mentioned, because it was a conductive material, we needed to implement a predictive model controller, or a Smith predictor. And with a KC of 80 and a tau I of 25 with the range of values plus or minus 5% for our process transform function, we were able to reach the 400 degrees Celsius in 5 minutes.